Okay, Hank. So it's kind of something we did the first week of school. So you have Hank to build pig pens for you. You checked in on his work every hour, and this is what you see. How many panels will I need to keep him busy for 80 hours? How about X hours? So your table, this would be hours, and this would be number of panels. And then let's go hour 4. It's gonna take 1, 2, 3, 4 panels. If you count these little panels, 5 is 1, 2, 3, 4, 5, 6, 7. If you count all the panels on hour 6, it's 10. Hour 7 is 13. So 4 hours gives you 4 panels. 5 hours gives you 7 panels. 6 hours gives you 10 panels. 7 hours gives you 13, and it keeps building just like that. So it's a pretty predictable build. This belongs to the linear family of functions. So every hour that goes by, you're just increasing the number of panels by 3. So 8 would give you 16, and so on and so forth. So the change, if it is the family of linear functions, the model is y equals mx plus b. So you need to find two things. You need to find the m and the b. And the y, in our case right here, would be the number of panels. And the x would be hours. So we've just got to find m and b. Okay, m is the slope. M is the change, how it's changing every hour, and it is changing up 3, up 3, up 3, up 3. So every time the hour changes 1, the panels grow by 3. So my m is 3, or 3 over 1, rise over run. Okay, now b is your y-intercept. That's what you start with. And you start always at 0. So I might have to work back to get to 0. So if I start working backwards, 3 hours. If I subtract 3, so now we're going this way, you're going to subtract 3, subtract 3, subtract 3. 2 hours is 1 subtract 3, which is a minus 2. 1 hour would be a minus 2 subtract 3, which is a minus 5. And 0 hours should be a minus 8. So my b is a minus 8. So my function is the number of the number of panels equals 3 times any hour you wish, and then after you times that, you need the minus 8. So if you're wondering about how many panels you're going to need for 80 hours, the number of panels equals 3 times 80, because every hour it goes up by 3, and that's 240. And then you got to figure out what you started with, and you actually started in the hole. You started with a negative 8, which is kind of not realistic in this case, but 240 minus 8 is 232. So for 80 hours, you're going to need 232 panels to keep him busy. Okay, so it's always a good idea to check your function. Y equals 3x minus 8. If we believe that is our function, let's check it. It'll only take a second, and you can verify that your work is correct. So if you take an x and plug it in for x, and a y and plug it in for y, you should get 16 equals 8 times 3 subtract 8. And 8 times 3 is 24. 24 minus 8 is 16, so it works. So you are very confident that your function is y equals 3x minus 8. Okay, the domain is all of your x's. So this right here is my domain. And the range is all of your y's. Okay, now the domain. What numbers, of all the numbers in the universe, what numbers are we gonna realistically use for the domain? And we will argue that we do not want to use this number right here. So after 8 hours have passed, we do not want to plug in 8.01, and we don't want to plug in 8.75 because it's hard to calculate how many exact panels you're going to need at 8 hours and 10 seconds or something. So for the domain, we want only to use whole numbers. And you could argue a couple things, and I'd probably give you credit. The domain, we only want 0 hours. That's kind of realistic. 1 hour, 2 hour. I only want whole number hours, nothing in between. So I want all of the elements in this set right here. The range, if you choose to match up with 0, 0 would give you a -8, and that really does not make sense. You can't have -8 panels. There's really no such thing as -8 panels, -5 panels, -3, 2 panels. I mean, really, this is the first realistic one right here. 1, 2, 3. ... So if you're gonna start with 0, you have to start with -8. If you don't want to include these negative panels, start with 1 panel. 1 matches up with 3, so then you'd have to start with 3 there, and I'd be fine either way. So you need to understand this. These whole numbers in this set communicates that you only use these numbers. Do not use any other number. If you do something like this, anything from 2 to 10, anything from 2 to 10, so you could use 2.05, 2.009. If it is something like this, this means you can use anything you want, any number between 2 and 10. You can use 2 because it's in a bracket, but you cannot use 10, so you have to stop at the number right before 10, which is 9.9999999999999, an infinite amount of 9s. Okay, next, let's recall how to play with these guys. These three are pretty tough. This one, the simpler version of this, its little sister would be like x squared times x cubed. And when you are multiplying powers, you must add the exponents to +3. But if you have x squared raised to the third, that is when you times exponents. So you gotta know when to times them, when to add them. Right now we're gonna add them. So we're gonna go x to the 2/3 add 1/2. And that's irrational, that's irrational. I mean, it's kind of a pain in the butt to add fractions. No one ever really likes doing that. Timesing's pretty easy, but adding's no good. So let's add them. Now this is 2/3. So they're measuring by thirds, and you have 2 of them that look like this. 1/3, 1/3. You got 2 of these thirds. And you got 1/2. So the units are thirds and the units are halves. And because they are different units, they're not like terms. You cannot add them. So you gotta get a little creative and change them to like terms. And the like term that we're gonna change them both to is sixths. Okay, so if we triple this guy, if we triple the top and triple the bottom, that would be 3/6, and we know that 3/6 is illegal because it's not reduced, it's not simplified to 1/2, but 1/2 and 3/6 are the same. 2/3, all we gotta do is double that, so times the top by 2 times the bottom by 2, and that's the same as 4/6. So if we have 4/6 plus 3/6, now they're like terms, you should end up with a total of x to the 7/6. That's a good problem. Okay, this next one, this is when we're going to times your exponents. So you've got x to the 1/2 times 2. Okay, timesing with fractions is pretty slick. It's not bad at all. It's easy because we don't care about the units. If this is halves and this is wholes, we don't care about the units. Times the numerators times the denominators. So you've got x to the 2 over 2, which is just x to the 1, and you don't even need to put the 1. And not bad. Okay, this next one looks kind of scary. Okay, good. Now we've got a negative exponent. You cannot ever have negative exponents. The fix is easy. Take it to the numerator and it will become positive. So let's start playing with it. Now this and this is nice. 35 divided by 7. That will simplify to 5 over 1. And kind of don't really need to write the 1. Ah man, your A's look kind of crappy. Let's save the A's for last. Let's do the B's. Okay, the B's. Now if I've got b to the 6 on top, I got 6 b's. Boom, 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 boom. And I got 4 b's on bottom. A b divided b is 1. A b divided b is 1. B divided b is 1. B divided b is 1. So I got a lot of 1s here. 4 1s. And you're left over with b squared on top. We move these c's to the top, so you got c3 on top. Okay, now let's do these a's. Okay, so there's a couple ways to do it. This b to the 6th on top and b to the 4th on bottom is really b to the 6 minus 4, and that is b squared. So when you're timesing, you add the exponents. When you're dividing, you subtract them. But I really like to prefer canceling them out, because that's really what's going on. So if you have a squared on top and on bottom you've got a to the 3/2. Okay, that's a fraction, but it's not a bad fraction. 3/2 is a half, a half, a half. It's 3 of them. So if you've got 3/2, that's the same thing as 1 whole and a half. That's the same as 1.5, 1 1/2. So what's 1 1/2 on the bottom is going to cancel out 1 1/2 on the bottom. Or what's 2 wholes subtract 1 1/2. And you are left with a to the half. So on top we have got a, and there is 1/2 left over. Okay, that's a good problem. Ooh. Okay, now they start to get kind of nasty. On top, you just gotta go step by step by step. It's like a 5-step problem. Let's do your numbers. 2 times 2, that results in a 4. Okay, let's times our x's. This is all times. Times, 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 times. So if you times your x's, right here I've really got x to the 1, and this is x to the 2, and that is x to the 1 plus 2. This is when you add them together. I've got y to the negative 2, y to the negative 2, so it's going to be y to the negative 2, add negative 2. Okay, your bottom, you need to take this negative 3 and times it to that and to that. So it's going to be x to the negative 6 and y to the negative 12. Okay, so I'm going to clean up this top a little bit. So I've got 4 times x cubed times y to the negative 4. And on bottom, I got x to the negative 6 and y to the negative 12. Okay, here we go. This is unacceptable, so I'm moving it to the bottom. This is unacceptable, I'm moving it to the top. This is unacceptable, I'm moving it to the top. So let's rearrange those pieces. So the 4 is cool, it stays on top. The x cubed is cool, it stays on top. I'm going to bring the y to the negative 4 to the bottom, and it becomes positive. X to the 6 to the top, and it becomes positive. Y to the minus 12 to the top, and no, I gotta go to the top. Y to the minus 12 to the top, and it becomes positive. Okay, now, here we go. One more step. We got 4 on top. That's done. Our x's on top, they're all on top. They all ended up on top, and we got 9 of them on top hanging out. Okay, we got some y's on bottom, some y's on top. 4 of these y's on bottom are going to kill 4 of these y's on top. So we really got y to the 8. And that is as far as you can go. That is simplified as far as you can go. That's an awesome problem. Okay, this next one. I'd do the parentheses first. You can clean up a lot of stuff inside the parentheses. Do the parentheses first before you start distributing, and then that's going to save you a ton of work. So here we go. Let's go this way this time. Okay, 2 times 2, so I got a 4. My y's, I've got 1 here, and I got minus 4 here, so I got y minus 3. And my x's, I got minus 4 here and I got 3 here. If you add them together, a minus 4, 4 negatives and 3 positives, that's x is going to be 1 negative. Okay, my bottom is already cleaned up. It's done. Y, x to the minus 1. Okay, now on the top. Step 2, you need to take this 3 to everything. You got to take it to the 4. The exponent of the 4 is 1. You got to take it to the y, got to take it to the x. So it is going to be 4 cubed y to the minus 9 x to the minus 3. And then on bottom we got y and x to the minus 1. Okay. Now, that's illegal, that's illegal, that's illegal. This one goes up, these two come down. So maybe not your final. We got 4 cubed on top, so that is 4 times 4 times 4. Calculator, or in your head, whatever you want. You gotta end up with 64. And then on the top you've got x to the 1, and on bottom you've got the y that's the original stayed there, and you're bringing 9 more down times y 9 to the 9, and you're bringing x cubed down. Okay, so 64 on top. One of these x's on top is going to undo one of the x's on bottom. So on the bottom I don't have a cube, I just got a square. And then your y's, y1 times y9 is going to be y10. And there we go. Next. Okay, this is like CC2, I think. Here I Excel CC2. So you've got 3 sets of data. You need to identify the family of functions. So your choices here are linear, quadratic, and exponential. And we taught you to identify them by figuring out how fast they're changing. How fast is the growth? So you They look kind of nasty. But look at let's look right here. If we start figuring out these decimals, kind of throw me off. So if I start right here at the 3, and then the 6, and then the 12, and the 24, if I just give you these, that's a pretty easy pattern to see. 3, 6, 12, 24. 3 doubled is 6, doubled is 12, doubled is 24, doubled is 48, double. So it looks like this one's doubling, doubling, doubling. Doubling is times by 2. That one is exponential. Exponential grows by times, or it shrinks by divide. And this one is growing, and every time it looks like they're all doubling. So that's not too bad. Okay, now this guy, if I start here, 1 to 7, that changed 6, 7 to 13, that changed 6, 13 to 19, that changed 6. Every time it looks like it's plus 6, plus 6, plus 6, that would be the linear. Linears are the easiest. They grow by add, and they add the same amount every time. Super predictable, pretty easy to work with. So this one's either, if you can use exponential again and linear again, or if you use one of them each, this one's got to be the quadratic. So let's prove it though. Let's see if we can figure it out. Okay, probably need a calculator. 0 to 14, that went up 14 times. 14 to 56. 56 take away 14, that went up 42 times. 56 to 126, 126 minus 56, that went up 70 times. Okay, 224 to 126, 224 minus 126, that went up 98 times. Okay, you could keep going, but it's definitely not linear, because linear would be plus 14, plus 14, plus 14. This one's kind of growing faster. It looks like each time it's increasing. So if you go again, 42 minus 14, 42 minus 14, that is 28. If we do this, if we do 70 minus 42, that is also 28. And if we do this, 90 minus 70, that's 28. Okay, this by definition is the quadratic. So the quadratics, as time goes on, they kind of get faster and faster. But the second change is constant. They're increasing 28, 28, 28, the second change. So that means it's quadratic. Okay, so the honors, you guys got to give me the equations. The rest of you kids go on. Let's do this. So in IXL, can't remember which one, CC3, quadratic was this, y equals ax squared, and that's, I'll just give you what IXL gave you. So a, because we've learned a little bit more actually, a is pretty easy to find. A is 14. Take 28 divided by 2, so your model would be y equals 14x squared. Okay, linear, we need m and b. M is 6 and b is, oh dude, suck. M is not 6. Okay, it's still going to be linear because it's plus 6, plus 6, plus 6, but over here, this is a trick question. These are not going by ones. We're jumping around here. 1 to 4, that's up 3. 4 to 7, that's up 3. 7 to 10, that's up 3. So I'm skipping because I went to look for the b, and the b is the starting dot. The b is what you start with at 0, and there was no 0, so then I got a little nervous, so we're skipping. Alright, so the m is not 6. Your m is rise over run. So it's 6 over 3. Your m is actually 2. So every time it's going up, not by 6, it's going up by 6 every third time. Every time it's going up by 2. So my 0, if I go down 2, my 0 is going to be a -1. So my b is -1. My m is 2. My function is y equals 2x minus 1. Okay, the exponential. So that was a trick question. Exponential. They taught you the model was y equals a b to the x. Okay, b is your rate of growth. B is how fast it's growing. And since it's doubling every time, my b is 2. And your a is right here. It's what you start with. So your function would be y equals 3 times 2 to the x. Or the x could go right with the 2. It doesn't really matter. You don't even really need parentheses, because this exponent only touches the 2. So it only affects the 2. It has nothing to do with the 3. Okay, good. Which expression represents an irrational number? Okay, the irrationals are most of these square roots that are nasty. 1 is awesome. So remember the rational versus the irrational. The most famous irrational is pi. It's a decimal that goes on forever, an infinite number of digits, but it's chaotic. It's hard to predict. There's no pattern in the digits. Square root of 2 is probably next, then square root of 3, square root of 4 is awesome. Square root of 5 sucks, square root of 6 sucks, square root of 9 is awesome. Rationals are whole numbers, 1, 2, 3, and they're also negatives, and they're also decimals that are nice and easy and predictable. So here we go. We're looking for irrational, so we're looking for these crazy numbers. We're looking for these decimals that if you try to show square root of 6 as a decimal, square root of 6 is, it's between 2 and 3, and it's like 2.449489743. I'm going to keep going forever. So that is rational, that is 2, and that is rational, that is 3, and 2 plus 3 is 5, and 5 is rational, so it's not D. That is rational, and this one is irrational. So if you have 4 ones, 4 ones is 1, 2, 3, 4. 4 ones plus 1 square root of 2. These are cool, but this one is no good. And if you add a rational to an irrational, your answer is just that, a rational plus an irrational. There's no way to add them. And a rational plus an irrational, because it has an irrational, it is considered irrational. So the answer is C. B is cool because square root of 4 over 9 is the same thing as square root of 4 over square root of 3, and that is a fraction. On top is a square root of 9. On top is a 2, and on bottom is a 3. So that's really the fraction 2/3, and 2/3 is cool, 5/12 is cool. Add them together, they're still going to be rational. And this square root is going to kill this square. So you're going to have a good fraction with a good fraction, and then the answer is going to be a good fraction. So C is the one that is irrational. Which statement is always true? The product of two irrationals is irrational. Okay, that is false, because if you take two irrationals, so if I take a square root of 3 and I times it, that's irrational by itself, square root of 3. that creates a square root of 9, which is awesome because that is rational. So the product is the answer of a times problem. So if I take two irrationals, I can create a rational. So that is not always true. Sometimes it is, because you can take square root of 3 times square root of 2, and that gives you square root of 6, and that still sucks. But it's not always true. Okay, B, the sum of two rational numbers will be either rational or irrational. Okay, if you take two rational numbers, so like 4 plus 3, it is always going to be rational. If you take even the worst of the rationals, 1/2 plus 1/3, your answer will still be a good fraction. You can take any fraction, add another fraction, your answer is still going to be a pretty decent fraction. So, the sum of two rationals can only be rational. So this one is definitely false, because you cannot take two rationals, add, and create a nasty number. The product of a non-zero rational and an irrational is irrational. Alright, here we go. The product of a non-zero rational, so that's like 4, times an irrational. If you do 4 times the square root of 2, your answer is 4 square roots of 2. The product of a non-zero rational and an irrational is irrational. I think it's C. I think if you take a good number and times it by a bad number, it is always going to be, the number will always be irrational. Let's check out D real quick. The sum of a rational and an irrational can be rational or irrational. It can always be one of the others. Man, I kind of like that one too. That one's good. The sum of a rational, so let's do a rational number, pick 4, and let's add to an irrational, square root 3. So if you add 4 and a square root of 3, your answer is, they're not like terms, 4 ones, and you got 1 square root of 3, your answer is just 4 ones and 1 square root of 3. If you add a rational to an irrational, it can be rational or irrational. This is irrational. God, D might be it. So, are we going to go for C or are we going to go for D? I wonder if we can prove one of them wrong. The product of a non-zero rational number and an irrational number is irrational. Non-zero rational. Well, I like both of them. I think they're both good. Now, this question is way harder than the question that's going to be on the test. So the review question, I'm not going to give you something like this on the test. I might ask you something like this. Take two irrational numbers. Oh, there we go. Take two irrationals and multiplication and create a rational. This is a good question. This is a way good one. Look at these 4 expressions. Figure out which one is going to end up being irrational. So this one might be a little too tough. I wouldn't worry don't spend too much time on this one right here. Okay, let's look at this guy. You have 3 functions. This one is linear. This one is cubic, and this one is exponential. Alright, so we've played with linear and we've played with exponential. We have not played anything with cubic. So let's see what the question wants. As x increases, which function is going to eventually have the greatest value? So as x gets bigger, the biggest x is 3, and it spits out a 24. This x spits out 27, and this x spits out 8. So this one was the smallest. Okay, now your linear is just adding 8 every time. So if we plug in 10 for this function, let's skip all the way down to 10. If you plug in 10, it's going to spit out 8 times 10. It's going to spit out 80. If you plug in 10 here, it wants you to do 10 cubed. That's 10 times 10 times 10. That spits out 1,000. If you plug in a 10 here, it wants you to do 2 to the 10. So that's 2 times 2 times 2 times 2, blah, 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 10 times. So I'm a calculator. I'm going to do 2 to the 10. And that is 1,024. So here's what you need to know. Exponentials, they may start out growing slow. 1 grows to a 2, grows to a 4, grows to a 8. But because they grow by multiplication, this is times 2 times 2 times, they are going to get huge. They're going to get big pretty quick. So if I keep going down the lists, as x gets bigger, this one is going to spit out the biggest numbers. Okay, let's look at these 3 kids. Rachel is this dotted line. Rachel's right here. Quinn is this one. And Steve is this one. So we're doing time. Oh, we're showing savings accounts. So we're doing time versus money. So Steve, whatever number this is, you could say this is $1,000. Steve's starts with 1,000 and he ends with 1,000. He never has more or less than 1,000. So Steve's money's not growing, it's not shrinking. So 1,000. Here is 1,000. It looks like Quinn and Rachel start off maybe with the same amount of money. Maybe they both start off with $100. Rachel's money is growing at a constant rate. So each month or year or whatever the interval is growing by the same amount. Over 1 month, up $100. Over 1 month, up $100. Over 1 month, up $100. Blah 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 blah. It's gonna take her some time to catch up to Steve. Now Quinn, he starts off with the same as Rachel, and then it kind of sits and sits, but then when it starts to build, it is gonna build. He is actually gonna get to 1,000 faster than Rachel. Rachel gets to 1,000 right here on the time. Maybe that's, who knows, 1 year. Quinn, his time matches up with maybe 8 months. He beats her to $1,000, and Quinn's money is the money you want, because it is going to take off and really start to grow. So, which statement is true? Rachel adds the same amount each week. Yes, that is true. Quinn contributes once and earns no interest. That is false. Let's go on to B. Rachel adds the same amount each month and earns no. Okay. Quinn earns compounding. Steve contributes once and earns no interest. That is it. So Quinn is earning compounding interest. Quinn's money is taking off way, way fast. Steve contributes once, and that's it. He's got no interest. So we're going to go with B. Okay. Look at these tables. looks like you've got a quadratic versus an exponential. And okay, polynomials. Polynomials are this. They're linear, x to the 1, x to the 2, x to the 3. This is linear, this is quadratic, this is cubic. Polynomials are any of these. Exponential is when your x is in the exponent spot. That is the definition of exponential. So here we go. What fact about polynomial versus exponential is illustrated here? Polynomial functions, that's these guys, are always larger. Okay, 4 is larger than 2, 9 is larger than 4, larger, 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 until you get right here. 49 is not larger than 64, so it's not A. Exponential functions are always larger. That's not true because 2 is not larger than 4. Polynomial functions grow faster. That's not true. Exponential functions grow faster. Yes, they will always grow faster. They grow the fastest overall, over time. Okay, here we go. We're gonna go, man, I've used too much time. Let's simplify these guys. Here we go. Okay, that's pretty sweet. Square root of 4 is 2. On bottom, we got this. Okay, now on bottom, it's illegal to have an irrational. So you cannot leave this on the bottom of a fraction. So you're going to times this by itself. Square root of 3, square root of 3 on top, and a square root of 3 on bottom. And that is 1. Times anything by 1 and you don't change it. So your top, you got to times 2 to the square root of 3. 2 is on the outside, 1 is on the outside, times 2 to 1. So it's 2 square roots of 3. On the bottom, times the outsides, 3 and 1, you got 3 square roots of 9. And a square root of 9 is just 3. So we got 2 square roots of 3, and on the bottom we've got 3 times 3. So here is what we got. On top we got 2 square roots of 3, and on the bottom is 9. That is your answer. Okay, I'm going to stop this and make a part 2, because if I go too long, I don't think it's going to fit on YouTube.